Okay, so this is the part of 15.3 that I did not get to in class. And I want you to make sure that you don't overcomplicate what I'm going to tell you. Because I just want you to know the main concept of this particular section. Okay? And mainly what I'm talking about is with snapshot graphs and what we're later going to call history graphs. So I hope the term snapshot is kind of familiar to you. You know, it's a freeze frame essentially of an object moving in and its position. Okay, so if we think of a wave on a string moving, okay, so some sort of wave here. Okay, I'm actually block this. So they show it moving left to right, but notice your axes here. Okay, essentially this is the height of the wave. So like its amplitude, right? How large it is versus its horizontal position. So like displacement. Okay. So I think this figure right here, 15.6, does an interesting way to explain this. Okay, so at a certain time, it's at this position. At another time interval, it's here. A third one, it's here. Okay, they do a good job of reminding you that like the change in displacement is the velocity times the difference in time between T2 and T1. So I don't want you to overcomplicate this. Notice that the amplitude did not change. Okay. And with waves, this velocity is constant, right? There's no like acceleration here. It's all constant. So essentially with a snapshot, know that it's height versus displacement. So it depends on it's describing its height with respect to its horizontal position in, at that moment. Now, the next one I want to talk about is history graph, put very, very shortly. So, a history graph history graph might make more sense to you. A history graph tracks kind of what we're more used to. Position. Okay, well, I'll be consistent in my wording. So basically the height of the wave with respect to time. Okay, so this is more probably what you're used to here. Alright, so here are 4 snapshot graphs. And you can see in the diagram how they make a history graph. Okay, history graph is y versus t. Okay, so height versus time. So you do not need to do this. Okay, I've never seen an AP question like this. It's very unintuitive. You kind of work backwards in order to do these. I don't particularly like them. I don't think it's the best use of your time. Okay, so basically, so we have snapshots, we have history. All of this will make sense when we tie these two together. So here we have some snapshot graphs. So this is y versus x, so not t. And this here is going to be a new word for us. Okay, so here we still have A for amplitude. Okay, so that's the height of the wave. But we need to learn what this term is here, wavelength. Okay, wavelength, okay, is the distance. Wavelength is also, this is called the Greek letter lambda. It's called lambda. And this equals wavelength. And wavelength is displacement, basically, from crest to crest of the wave. And the crest is kind of another way of saying amplitude. Okay, so if it's at the top, if it is above the x-axis, we call it the crest. If it is below, we call it the trough. So just words that should be a little familiar with. So even though this is plotted against position, remember it does still depend on time, right? Kind of because of this relationship here, because this change in position that's happening, right? You see how it is shifted here. It moves from this position and it moved a certain distance, right? It moved because, it has a velocity. It's moving. Time passes by. So this wave currently is moving this way, as we can see. Okay, so before we looked at snapshots, and this is a graph of, this is a history graph. Okay, because it is the height of the wave versus how much time has passed. Okay, and the main thing here is, well, if this axis is time, then this measurement from crest to crest, right, when it was position, we called it the wavelength. This is the wave that we're more familiar with. This is the period, right? So that should be a little familiar from the previous chapter 14. And speaking of chapter 14, from simple harmonic motion, okay, so with simple harmonic motion, we were usually talking about horizontal motion, with springs and things. And so remember, this was a cosine 2 pi ft, or sorry, little t, not period, or that's the same thing as saying 2 pi small t over big T, period. So this is what I want you to look at here is, this is the graph of just a history graph. And you can read this in your book. But look, this is exactly like the simple harmonic equation, except for it is describing particularly the height of the wave. Okay, so this part looks familiar. Okay, and this one comes from this snapshot. So notice that this depends on x, this depends on time. And you can see that this is very, very similar. Okay, this is a function of position here. This is a function of time. Really, the only difference is here. So the current time over the period and the current position over the wavelength. So remember, when we looked at those graphs, wavelength and period, right, they represent the same part of the wave from crest to crest. Okay? T represents the current time, X represents the current position. So mathematically, like, these are essentially describing the same thing here. So, and this we finally get to kind of the point of this section is, you know, what happens if we describe this both as a function of position and time. So we have two variables, right? Two variables that are changing, x and t. So it's current position, it's current time. And what I want you to realize here is we just kind of combine those two. And, you know, if you've done any transposing of graphs, you know, in math class, then hopefully this looks a little familiar. Okay, notice this minus sign here. Okay, don't get confused. This means it is moving to the right, so its velocity is to the right here. Here, this is the opposite. It is moving to the left. Velocity is to the left. And the final thing that I want to go over is, you know, is there a way that we can tie together the wavelength and the period? You know, how do we, both of these describe the movement of a traveling wave? If it's traveling, right, it has a velocity. So how are we going to find this velocity of this wave? And so if we go down to the basic definition of an object moving at a constant speed, right, it's distance over time. Well, the change in distance, right, if we go back to our snapshot graph, right, the distance from crest to crest is the wavelength. So this is lambda, remember. Okay, this is still in meters. Okay, there's nothing fancy there. And it's over t, right, for period. So this is still meters per second as far as units. Okay. But more commonly, you will see this rewritten. So because t is equal to 1 over f, most commonly you will see this written like this. Okay, so the velocity of a wave is equal to its wavelength times the frequency of the wave. And we will look at this much more when we talk about light, especially. Okay, thank you.